Okay. Hi, everyone. Thanks for being there. So my talk is going to be a little less serious because it's all about chit-chatting and dialogue, but it's also very fun to do. And there is a lot of common points, I think. At least we're using bit pair encoding. That's one common point. So our team, we are a startup. We are based in New York. This is our team. We raised a little bit of money. I took that from an investor pitch test, so it's a bit serious, but yeah, just so you know. We are building a social AI that's made to hold long conversation, to be fun, to care about you. So it's a dialogue system. It's a bit different than what I'm going to talk about tonight, because the topic of today is chit-chat. So chit-chat, what is it? It's a small dialogue. And the rules are open domain. You can talk about anything you want with a robot, with a bot. But it has to be short. It's like less than 10 turns. It's small talk, shallow topic, just chit-chatting. So you won't go very deep on like what is the reason everybody's living on Earth and does God exist? Even though everybody wants to try to ask that to chit-chat systems. So there are two ways to do chit-chat systems. One is retrieval-based model. It means you try to get a big data set of dialogues, the biggest you can, so like Reddit or you can ask mechanical Turkers to write dialogues. And then when the human asks something, you try to compute a similarity between your dialogue, your like database, and the last utterance, and you take the closest one. So that's what like everybody was doing. So that's the basis for a lot of bots you can use on the internet. And another one is generative models. So that's more recent. This came with like the advance of deep learning and like systems which were able to generate words, like LSTM. And the idea here is that you generate word after word until you get a full utterance, and then you send that. So typically it's an LSTM that will do that. And I was like it's sparked a lot of research. This paper with this kind of thing where like they show that when they ask what is the purpose of life to their bot, then this could generate like sentences that made sense just word by word. So that was a bit. And yeah, so since then there has been a lot of work in this field. So these two kind of systems have strengths and limitations that are different. So retrieval models usually have a good grammaticality. Basically, all the replies are written by humans, so they sound natural, but they can't really adapt the response to the context. If you don't have the exact response in your database, you're screwed up. And they have a problem with consistency. You have this question of how do you make a vector from your sentence? How do you compute that? And usually it happens that contradictory answers, for example, are very close to the same question. So if you ask, do you have a cat? Like the answer, yes, I have a cat, and no, I have a cat, are very close, both in the database, because you're just talking about the same topic. So like they tend to say, to contradict themselves all the time. You ask, do you have a cat? Yes. Next time, do you have a cat? No. Yeah, so makes no sense. And the generative model, the cool thing is that they can adapt to the context. So that's very good. But they have a tendency to be a bit shy. So they would say, I don't know. They would take the safe answer always, because it's a matter of probability. And like, I don't know, is always kind of plausible. So they tend to be very, very shy. And the grammaticality can be an issue, because they generate word by word. They have to learn how syntax language works. That's a lot of work to learn. So the idea of NIPS conversation. So if you don't know, NIPS is a big machine learning conference that's happening every year. And it's like really the highest place for the hype of deep learning. And so this year they were doing this Conversational Intelligence Challenge 2. So what's the competition about? It's a dialogue. Everybody has a few sentences of persona. So this is like, this defines your life. And this is the life of the bot. And you're supposed to talk with the bot, acting as if you were this person. The bot is supposed to talk, acting as if it was this person. And the idea here is to enforce consistency. Everybody has a fixed personality, and you're supposed to stick to it. If you have a cat, you have a cat. You can't say no. And so Facebook created a big data set asking mechanical turkers to play this game, talk to each other. So it's a nice data set. Here you see an example. It's a nice data set, but it's also quite specific because they ask the people to try to talk about their life and question the life of the other. It's a data set with a lot of questions, like people asking, what are you doing? It's quite. And also a lot of people talking about themselves, so you will see. But yeah, so that was a game. Yeah, I'll put that a bit. So that's a bit old actually. There are a lot more teams now. So that was that's the leaderboard. So our system is the one on the top. That's the first submission, not so good. A bit better right now. So we get very good results. Yeah, just show you a bit what are this kind of metrics. So getting the apple is good. That means you're the first for each metrics. PPL, I'll just explain you very quickly what does this mean. PPL is how well you can predict the next word. Like if I give you the beginning of the sentence, how good are you to predict the next one? Hit that one is how you can detect the good answer among 20. Is how many content would you say? How many content words are common with a good answer? So maybe I just show you how this works in real life. Let's see. So in this dialogue system, we have very high expectation because we always talk a lot. So we think dialogue is quite easy to do. We're like, yeah, that's just talking. So everybody can do that. But no, it's really hard. it's a bit harder than the translation for some aspect because you have to keep consistency over a lot of sentences. Right. A dialogue flow is a very big part of dialogue. So this is like the sec-to-sec system. So it's like the current major state-of-the-art system. That was the paper I showed you. So this one has little personality. It's a surfer. Yeah, let's take a new one. I've been talking to this one earlier. Okay. This one graduated from college. He wants to play basketball. He had a knee surgery, 7 foot tall, hoping to play. Okay. So, hi there. You can give me a message if you want to ask stuff. Oh, wait, that's too big. Yeah. I am saying how good. I'm fine, thanks. What do you want to ask him this time? What? Yeah. So that's a bit strange, right? Yeah. So you can add the artificial delay, but that's just 2 LSTM, so it goes very quickly. It eats my 4 words, and it's spit out its 10 words, so it's very quick. So I put them on 2 GPUs on the internet. So this one is quite okay. What are you doing? Just show you a few sentences so you have a grasp of what's the current state of the art here. I'm just practicing my computer. Now, what's your name? Yeah. Now, how are you doing? So now it's a bit off. Do you have an idea for something to ask it? How old are you? I'm doing well. Now let's try the main question I usually ask them. What is the meaning of life? I'm a bit tired. Okay. Thanks. So it's really hard. Usually, either you have when you have good grammaticality. Still it's generating word by word, and it's English, right? It's not like a random shuffle word. So there is something, but it's really hard for it to. And it's also remember a bit from the personality. It tells me it has the knee surgery, so there is some conditioning, but it has some difficulty to listen to me, basically. Let's take the main one. So I have a different personality every name. Let's take Chatty. So this is our system. So it's random, so basically maybe it will just not work right now. It's sampling responses. So I'm not saying it's going to be really great. And definitely there is still a lot of problems, and I'll show you. So now it takes some time because it's like a fat model, which is more natural, you know, like the, how are you today? I'm great. How are you? Have you been up to? I feel stressed, like when I see my kids, you know, trying very difficult sport things. I'm like, do it. I just finished playing basketball. What do you do for a living? Anybody has an idea for a job? Spider-Man. Oh, I don't know if you're Spider-Man. Okay, let's try it. I'm Spider-Man. That's a cool name. Yeah, I mean, makes sense. What were you studying? Basketball. Okay, I guess. So see, it makes quite a lot more sense, I would say. We have a good conversation tonight. Soccer? Yeah, that's straight on English corpus, so let's say baseball. Baseball doesn't mean anything. Okay, I won't make it too long. I like baseball. I love baseball. Do you have any kids? Yeah, I have 2 kids. That's awesome. I hope to play yours. Okay. Okay, let's do last one. Have you ever been to Europe? No, but I want to go to Italy one day. What about you? See, one cool stuff too that I like is that it's totally out of the personality, but it's like creating stuff that makes sense. So yeah, that's cool. Let's do this little one. What's the meaning of life? Usually it doesn't work, but I did it for the other one. So you have another question you want to ask before we say goodbye?
What's my name?
What's your name?
What's my name?
Oh, my name?
Does he remember?
Ah, yeah. That's tough one. I think that's the meaning of life. Okay. What is your favorite food? What's my name? My name is Sarah. What is yours? Yeah, I mean, it could make sense, actually. What's my name? My name is Sarah. What is yours? Hi, Sarah. I'm Tom.
He doesn't remember.
Ah, yes, you're right. So it only remembers 5 sentences. Yeah, so that's gone in the limbo. In limbo. Yeah, we should do more. I had 1 week 7, but usually I also forget after 5 sentences. So I just don't notice it. You see, I just forget that it was supposed to be cool. I'm John. Yeah, that's hard. Oh no, let's see. Okay. And I discovered just earlier I was doing with playing with Theo, and we discovered he can speak French. That was funny because it's trained on no French data, but maybe by pair encoding. But yeah, just showing you. That's just really funny. That's a funny discovery, and just this afternoon. Like last time I said je vais à l'école, and he asked me, do you like school? I said, wow. Ah, parles-tu français? Okay. Well, okay, I should switch to the rest of the presentation. So that was just to show you the difference. Yeah, oh, this one doesn't go first. Okay, the other one, that was fun. Okay, I'm back. Yeah, so what's the difference? That's now what you're asking. So I assume you know a bit like LSTM sec to sec, so I won't explain all this whole thing. You can check. That was the first one. So this new. Yeah, so that's what we. There is a. So the main difficulty on this is that you can have. There is a personal chat is quite a small data set. So basically, you end up in 2 settings. Either you have a large model that is overfitting. This is the blue one, which means you can tune your model to get very good results on a public data set. And we try it when you try it on some hidden sentences, like right now we are doing a dialogue that it has never seen. That's like a private dialogue, new dialogue. And usually this model, they just crash because they are really tuned on their training set or validation set. And they can't generalize. And the other hypothesis, the other possibility is to take a small model, then it's quite bad, but it stays quite bad also. So that's the orange one. And our model is just good and good. So the secret is transfer learning. So what is transfer learning? So first, our model is transformer model. I just show you very quickly. So it's like not like an LSTM. It takes a fixed number of inputs and it outputs a sequence of the same length that is supposed to be the probability for the next word. So like Bob, this will be the next word after Bob, which is. His will be very, and like very happy. So this like this. You put the beginning of the sentence, it output the next words. And how you do that is you do self-attention. So you compute a lot of attention here, causal attention with causal masking to predict the next word. And the tricky thing is to train it the right way. So as I said, the competition data set, wow, there's a lot of words on this slide, sorry. So the competition data sets, it's big data sets, but it's still very small to learn all you need to learn for Dialog. For Dialog, you need to learn like the reference resolution. When you say he, I was talking about the guy I just mentioned before. You need to learn topic coherence. You need to learn a sentiment analysis, like I didn't try, but if you said it like my dad died, you will say, oh, I'm sorry. You need to learn all this. And it's really hard to learn all this for a small data set from a small data set. So we use transfer learning. First, we train the model on a language modeling task on a very huge data sets. So it's the one we use is a lot of words again, sorry. The one we use is the Toronto book data sets. So it's like 7,000 full books written by people who couldn't get them to be published. So they put them on the internet. So it's mainly romance and fantasy, so it gives us a little cheesy model. It likes to talk about love and relationship, and that it learned to predict the next word over these 7,000 books. And to be able to predict the next word, it needs to learn coherence, sentiment, all this. And then, when it's trained on these 7,000 books, we fine-tune it on dialogues. So yeah, as I said, now we have a model that have a basic notion of common sense, sentiments, all these. And we need to train it that in the real life, there is dialogue with two persons talking. So we build sentences, yeah, like this. We input its personality, the history of the dialogue, and the last sentence. We put that in the model, and we predict the next word. And we learn like embeddings that are specific to each one of the speaker. So these yellow and purple thing are embeddings that we learn. That means these words was said by this guy. And you can play with these learned embeddings in funny way. Yeah, that's a bit complex. So you can, because transformers don't have an inherent notion of position, you can use this positional embedding to say, this is like something that could be in the beginning or the end of the sentence. Because like a personality is not something that is really in the beginning of the dialogue. It's like a common background over all the dialogue. So we can try to put that in these embeddings. That's how we do. And then we learn the dialogue flow, which is, we take all the gold dialogue written by the Turker, and we train the model to predict whether we put a full dialogue, and then we put the real last utterance that was said by a human, or we put a distractor, which is like a random utterance. How old are you today? You have a nice dog. And we train it to predict that this is a bad answer. So there is a classifier that say, yeah, this is bad or this is good. And yeah, that's just. And then we need to talk to human. So there is a little bit of beam search. Beam search means when you predict the next word, sometimes you won't take the most probable word because there is like a word that is not so probable, but it will lead you to a good direction for the rest of the conversation. You know? Like a word is a bit complicated, but after this word, you will be very happy to say this good word that you are preparing. You know? So that's called beam search decoding. And that's it.
Thank you, Thomas. Do anyone have a question?
Thank you for the for the talk. Very nice.
was mainly a demo.
I know that you have consistency problems. Do you try ontology reasoning? Ontology reasoning are specialized in solving this consistency problem. Do you think there is a solution to correct the consistency problem with ontology? So
Yeah, I think so. Yeah, there is several
pretty
ways. So
common in NLP.
So this unsupervised learning of language model over a lot of books give you like good results on common sense testing, and then so that's usually what we use to encode common sense. Then for consistency, for example, when you say your name, we should probably just take it, identify. I don't know how to do that, but like identify some sentence to keep it in the persona or something like that to say this is important thing to remember during the dialogue. And there is some parts you can just forget. So that's the way we would be, I think, trying to do this. Yeah.
Okay. So no ontology building or something like that.
Yeah, I don't know. I'm very cautious when it comes to putting too much thinking. I think deep learning end-to-end thing. Like I tried many like smart way to do linguistically smart thing, and just in the end, just pure brute learning was just the best. So if you could generate your ontology just putting some bias that would let your model learn an ontology on itself, there I would go for there. Like plugging ontology, I don't think that would be super interesting. Right now what I'm really interested in is trying to get some personality for the other, because it has its own personality that it remembers, but it don't remembers yours. It's only from the dialogue. But in the real dialogue, you're trying to learn, two things. You have your knowledge, your personality, but you're also trying to learn a model of the other knowledge. So that's something I find very interesting.
Some other question?
Thank you. Yeah, I just have two small questions. The first one, I was wondering why you choose the strategy just only to predict the next word for the language modeling instead of the context.
Yeah. Well, context has a lot of possible interpretation.
For example, the word, you have the left word and the right word.
Yeah.
Like for
like
example, word embedding or something.
Like word to vex thing. Yeah.
Yeah, right.
So language modeling is like currently it's the easiest way to train a model on a very huge amount of data. It's very simple to implement. Just take your huge amount, you shift the words by one token left, and you have your input and outputs. But the funny thing is that we discovered that by making it predict more, see here we train it to learn the full next utterance also at the end when I was showing these classification settings here. And making it learn to predict the full next utterance actually improved the language modeling thing, Instead of just learning to predict next word, it learns to predict some kind of semantic vectors of the next word. Well, it's not because it's a transformer, but and having a long context help the language modeling thing. So that's something we studied a small research project on to see if it's like a general thing that could be interesting. So making longer context. But like the previous word is usually not so interesting because it's already in the memory of the language model. So yeah.
Okay.
But there is interesting thing. So the main idea to keep is that we want to be learning all this unsupervised because we want to be able to learn on very huge data sets. So yeah, that's the main idea.
And the second question is, I saw at the beginning, the task is like a retrieval task. And here, I saw that you use the classification loss. Why do you, why you don't use the ranking loss, for example, for the retrieval task?
Retrieval model is another type of model, yeah. I was talking about these two paradigms. So we're on the second one. We like this purely generative models. We generate word after word. But it's trained in a retrieval settings, right? There is some common idea. And it could be used as a retrieval model too, because this classifier can identify a good answer with regard to a bad one. The thing is that that's very heavy. You saw the time it took to compute, just one answer. So usually retrieval models, you have like 5 million possible iterants in your database. So if you take 2 seconds to compute one similarity, it's a bit long, right? But there is an interesting thing right there. But you're right, it's trained in retrieval settings somehow.
Okay, thank you.
Hello. I want to know if the model is being able to learn on the real time by doing for the dialogues you just made with the agent. Is it be able to learn in the real time? And if it's been able to learn, how you're going to like justify that this question and this response is a good input for the model?
Yeah. So Microsoft tried to do that with TAE. It was an experiment. But you could add on a robot to human way. Like you say, this is a gold response. Well, if you're on Mechanical Turk, usually it's just a bad response for somebody who is not paid enough and just want to put. But if you have like a real, like, here I'm talking French, so it's also bad. But yeah, you could use that. But then you have all the problem of continual learning, like catastrophic forgetting. You've heard about that, so you know. So the things that the model tend to forget what happened before. So there's a lot of research on that. Continual learning, lifelong learning. How do you learn new things without forgetting what was before? So that's super interesting. We've done some stuff on that earlier this year, not on this model, but yeah, you could do that. You could do that.
Yeah, you said something like you were using different embeddings for different peoples. Could you explain how you, what embeddings are you talking about? And
all my technical explanations were very bad, I'm sorry. I was too focused on just chatting with the model. So I can take some time to explain that if you want. So usually in LSTM, you don't need to explain the position because the model eats words after words. So you just know, like, the words I've already eaten are in the past, and the word I'm eating now is the current word, okay? For Transformer, it's not so easy, actually, because it's eating all the words at the same time. All the words are put in the same time, and then it's all about attention, but attention is not position-specific. Attention means just basically, I will take this vector, make a scalar product with this one, and the scalar product could be the other way around. It doesn't change, it's just a scalar product, well, a dot product. And so how do you make it aware of where is the beginning of the sentence, where is the end? So there are several ways you can do that. But the way we do that is that it learns additional embedding. So this is the word embedding here. It's a vector that is associated to I. And this is a positional embedding. So it's also another vector, but it's always the same at the beginning of the sentence. This one is always the same for every sentence. So it learns these positional embeddings that it used to do positional retrieval, like to know this word is about in the middle because that's like an orange positional embedding. So what we thought is that we could just add another set of embeddings, which are like this green one. It's also another vector, and it will learn it to say that, yeah, this is like personality. This is like a sentence that's diffuse, you know, or that's what we wanted to learn. And this yellow, it would always be yellow every time it's speaker one talking. So it will learn that yellow is related to speaker one. So this is like 3 matrices that you plug together. You just sum this, and that's the input to your transformer.
And is the personality embedding trained on the sentence of the speaker, or it's just?
It's trained, yeah.
It's trained?
Yeah, it's trained during the dialogue training, which is the second phases of training. And the cool thing is that you can manipulate these embeddings. For example, one bad thing is that when you put this 4 personality sentence, you don't really want it to think that, yeah, that's the last sentence. That's very important that it's the last sentence. No, it's not really important. It's just there. So you could just put your positional embeddings and just repeat them. So it will say, yeah, that's the beginning. And that's also a beginning, you know. That's also a beginning. So you can manipulate the position. So I think that was a nice idea. But actually what worked as well was just to augment the data set by randomizing the order of the personality. And that's just pretty much the same.
Thank you.
Because I don't really believe in sentence embeddings.
I understand, but I mean, for these sentences, that seems okay. You know, I'm sure you can get embeddings for that.
I mean, that's what the other people do in Convai, like the baseline of profile memory. This one, it's quite good. I mean, it's 55%, so it means every other time you get the good one. So this one compute LSTM over each sentence of personality, and you take the last hidden state. That's what you.
You mean you get an embedding for each sentence, and they feed these embeddings to the same LSTM, for instance?
Yeah, that's something like that. Then they have attention over the possibility.
Okay. But do they have this notion of sentence order as well, or?
No, then you don't have this. You have this memory. You have several slots,
Yeah, okay.
and you compute the embeddings for each personality, and you just take the last hidden state, and you make an attention over it, and then you have a regular LSTM for the sentence. But I think it's really hard to cram a lot in a sentence embeddings. And I think with this idea of like being independent of the order, you could stack a lot of things.
But don't you have like some issue of? I mean, how many sentences like this do you have to like stack together? Don't you
Yeah,
have some
there's a. But also in LSTM, I mean, you don't remember 1 million tokens. So here the input is 512 tokens, and actually we don't use all this. So that's the input of the pre-trained model, and we only use like 300 tokens to put all this 5 sentences and like 5 exchanges of history. You have a lot of room, I think. But we were talking with, like, I was talking with Theo this afternoon, say, yeah, can you put 100 sentences of persona? Yeah, no, you cannot. But the life of a bot is not so complicated. Like, it could be described by 5.
Anyone else? I have a question.
Oh.
So you design your models for a competition, but how far is it from production for applying it in your application, for example?
Yeah, so that's a good question. Because when we saw it was very good, we were like, yeah, we should use it. Because we use a system that's very different in production. So the main problem is the computational power needed. So this model is 160 million parameters, so that's a lot. It takes like just one GPU to generate an answer in 1 second. So if you want to scale it to 10,000 users, you will need just 10,000 GPU. So everybody will have this GPU. So that's the main problem. But that's something we want to investigate. How far can you reduce the size of the model without losing all the common sense knowledge and all the things you want?
Thank you, Thomas.
Thank you.
So thank you to Xebia for hosting this meetup. Thanks again, Guillaume and Thomas. And we are inviting to have a beer, and we just have to leave before 10 p.m. Thank you.